Wei-Cheng Zhang is a PhD student at CMU,
Yeah.
working on and talking about the deep learning approach to XC text classification. Right?
Hello, everyone. This is Wei-Cheng Zhang, currently PhD student from LTI CMU. First, I would like to thank the workshop organizer inviting my advisor, Yimin Yang, to present this talk. However, due to some personal traveling issues, she cannot make it. So today, I'm going to talk about the deep learning approach to extreme multi-label classification. This is a joint work by Jing Zhou, Yuexin, Yiming, and me. So this talk is divided in two folds. The first half, we focus on our SIG-IR 2017 paper in earlier this year, which is about using deep learning architecture to extract richer feature representation for multi-label text classification. And the second half, we introduce some related work in deep structured learning paper in this ICML. They can also be used to apply on multi-label classification. So to start with, let me briefly introduce the definition of multi-label text classification, XMTC in short. So it's about finding and document its most relevant subset of labels from a very large space of category. So this is different from the multi-class where each document only have one label. So I believe everyone knows this. So introduce about the notation. In our setting, the training data is denoted as a XY pair. X is the data, Y is the label, and our goal is finding a mapping from X to Y. So what's so special in XMTC? So in multi-label, extreme multi-labels, typically it refers the label space is very large. But actually, if you look at the XMTC datasets, it's also that the number of document N and number of feature D are also in extreme scale. So this poses two key challenges. The first one is scalability, both in terms of training and testing. And another issue is the data sparsity in terms of many labels only appear in very few documents. So in this talk, we try to provide solution for these two challenge in XMTC. The first one is we will discuss how to extract another way to extract feature representation besides the traditional back-and-forth method. And the second half, we will discuss how to exploit label dependencies. First, in the literature of extreme classification, we can roughly divide the approach into two categories. The first one is target embedding, and the second one is tree-based ensemble. So I believe I don't need to give more detail on these two parts because this is the traditional state-of-the-art in this extreme classification. What I would like to focus on is the deep learning approach, because this may be less familiar with the extreme multi-class classification community. So in this talk, we re-examine the state-of-the-art XMTC by conducting a comparative evaluation of 7 state-of-the-art methods, including the target embedding and methods and tree-based method and deep learning methods. So to start with, let's look at the XML-CNN, which is a very famous convolution network on text classification. So the thing is, instead of using just back-of-word feature, the raw text is fed into the model, as you can see in the figure here, the resolution may not be that good. So here is a sequence of word, and each word is replaced by the word embedding. So you have a vector here, it's a word embedding with the associated word. So the input will form a n by k matrix, where n is number of word in a document and k is dimension of the word embedding. So since the input is n by k, you can think of this like image, and we are doing convolutional filters on this image. So what they do is they place a convolution filter, 1D convolution filter, sliding through the time dimension. So this is implicitly it's extracting a generalized version of the n-gram features compared to the traditional backup or bigram or trigram features. After obtaining the feature map here, they also use in this red box here, they are using the filter size of 2, but you can also use 3 and 4 and so on. So that way you're extracting more generalized bigram or trigram features. So after that you have a feature map, and what they do, they just do max pooling to extract the most strongest signal in that feature map and stack them all together, and finally is the fully connect layer. So this is a brief introduction of the current strongest method in multi-class classification. So what we did here in the extreme multi-label classification is there are several different parts, roughly 3. Let me go through them one by one. So the first part is the convolution. As you can see, the red box is the convolution filter. We slide through the convolution filter in another dimension. So maybe we can go back a little bit. So in the previous work, they slide through the convolution filter in a temporal manner. Here, we do it opposite direction, that we swipe through the convolution filter through the word embedding dimension. That is, you can think of in an image, it's a spatial dimension. So the motivation is like each filters is capturing more global information given the whole sequence. So sliding through different dimensions of the word embedding is like capturing the most salient features of word among the entire document. So we also have, filter of size 2, 4, 8, etc., that capturing different spatial relations among the word embedding matrix. So after that, we also have a feature map. What we do is not the traditional max pooling. What we do is like adaptive max pooling that extract, say, 2 to 3 most significant features in the feature map. So if we are doing that, the final feature representation here will be even 2 to 3 times larger than the previous method. So in the extreme multi-label setting, we know that the final output number of label here is very huge. So we need to make a low-rank matrix factorization here, so that there's a, say, 512 hidden representation in the middle that first project this long feature map to a lower dimension, and then we do fully connect. And just as a case study of the memory consumption, since, say, you may be interested in how large the memory consumption of these neural nets. So say we are using vocabulary size 30K, and the word embedding dimension is 300, and we cut the document length to, say, 500, and we analyze the largest data set. The number of label is 670K, which is the largest data set on the website, and we set the hidden dimension to 500, and the pooling units to 128. So first is the embedding layer. The number of parameters is roughly V times D, roughly 9 millions. And the number of parameter in the convolution layer, it's calculated in this way, because we have, for the filter size of 2, we have 32 of them. For the filter size of 4 and 8, we also have 32 copy of them. So in total, it's roughly 200K. And in the hidden layer, I'm referred to the parameter in this part, in this hidden layer. There is, we fixed out the max pulling output to be 128. And given that we have 32, each have 3, times the output 500, that's roughly 6.3 million. And the bottleneck is actually on the final output layer. That is the 500 times 670K, which is roughly 343 millions. So if you sum this all up, this roughly accounts to 360 million number of parameters. So if you're using floating precision, that's roughly 1.3 gigabytes. Doesn't sound that bad. If you have a 12 giga GPU memory, or you have more, this definitely can fit into your machine. So the analysis here is just the minimum of memory you use, because when you are doing backpropagation and the mini batches, that also depends on the mini batch size you use. So finally, it's the choice of the loss function. We know that if in the multi-class classification, if you use softmax, the model will favor only one label and pushing other label to 0. So in the XMTC setting, you will mostly put 0 probability output on the other labels. But actually in this kind of data set, because each document is only tagged with the most relevant, say, 5 or 10 labels, doesn't mean that other label is not relevant. So this using softmax may not be that good choice. So we consider the most naive binary cross entropy using the sigmoid. So okay, finally, it's the experiment setting. So we consider 6 benchmark data set. The first two is small data set, RCV1 and Eurolex. And the middle two is the medium-sized data set, Amazon 12K and Wiki 30K. And the last two is the largest one, Amazon 670K and the Wiki 500K. And here is the results. In XMTC, we usually most interested in the top portion of the rank label. So the results are evaluated by precision 135 and NDCG 135. Here we present the precision 135. So you can see each column representing a method. The boldface indicate the best results on that row. So each row is a data set, and the boldface is the best one. So we also, the start notation denotes not statistically significant, different from the best model on that row using the sample t-test. So you can see here there's no star because all the results are statistical significant. Among 18 rows, so the XML-CNN is the proposed method. It has the best score in 10 rows. So while the second method, Sleek, has 4 best rows, and then followed by the fast XML. To be honest, the training time for the XML-CNN will be a lot slower than the fast XML, the tree-based ensemble method. So let's look at the NDCG. So NDCG also provides similar results, but you can see here the star notation here and here. That means that this is not statistically significant compared to this one. Finally, we study the ablation test because we have a close relationship with the previous work with the Kim-CNN. So we conduct ablation tests building upon the Kim-CNN, adding one component at a time. So the lightest color probably the white here in the screen is the Kim-CNN, and if as the color grows darker, it's a different version. So from the light to from the white to the lighter one, we changed the softmax to binary cross entropy. As you can see, that gives us some gain in this data set and this data set, but probably not this one, in the precision one. And the version 2 is we add a middle bottom hidden layer. So this also will give us some gain in the performance. And finally, it changed the convolution direction from temporal to spatial swiping direction. So that you can see in this data set give us the most improvement. And also this one data set. So this is my first half of the talk. In the second half, we investigate some recent works using deep structural prediction framework to solve the multi-label classification problem. So from now, the work is published by other people in ICML. So we run the experiments and compare them with the state-of-the-art method in extreme multi-label classification. So so far what we did is we are given an input X, we pass through some function, and we extract the feature representation. In the final layer, we simply use binary logistic regression to predict the output independently. That's so far what I have described. So from next, we discuss a structure prediction thinking of doing multi-label classification. So you can think of here, what they do is they try in the structure prediction, they will extract joint feature representation from both the data and the label. And what they do is finding a prediction output Y that has a lower energy. So this corresponding to finding the largest conditional likelihood of Py given X in the traditional graphical model, CRF, those kind of thing. So the motivation is that they want to extract joint feature between the data X and the output and explore the label dependency via the design of the energy network. So the key is how you design the energy network here. So this is, let's look at each component of the energy network. They're designed in David ICML paper. So first, it's a feature network that extracting the feature given the feature input X. It's just a two-layer MLP. Next is the energy network. It's composed by two parts, the local energy and the global one. The local one is in the middle, you can see here in the middle part of the figure, it's a sum of the L linear model, where L is a number of labels. So this is very similar to what we did in the previous work. It's just BI is a lower dimensional embedding to learn for each label. And in the upper part is the global energy. So what that means by global, it's the score function is independent of X, but you can see here the formula here is trying to extract the lower embedding of the large output space Y. By that, we hope that we can learn some affine transformation of the output that captured the salient feature of labels using this to model the label dependencies. So the final energy design is the local part adding the global part. So how do we learn the model parameter theta? So say we are simply using the mean square loss as the loss function here. First, we need to find the prediction yi hat by solving the inference problem and of the energy network given the fixed model parameter theta. So exact solving the inference may not be feasible. So what they do in practice, they just do gradient descent with a fixed maximum iteration number, say just 5. So they do this 5 times, obtaining the prediction y hat and fix that to calculate the gradient based on theta. So actually calculating the gradient with respect to model parameter theta could be somehow tricky. So let's look at the computational graph here. The input is x, and you pass this through some feature network. You catch the feature, and you will calculate you first make a forward path based on this to calculate the prediction y. So you need to calculate the gradient with respect to y here. In the pink box is the model part. But in the backward path, you also want to calculate the gradient with respect to the model parameter theta. So you need to visit multiple times through the pink box. Like for example, the first path is like this, and the second part is like this. Because the yi is sort of like the RN thinking that the final prediction of y is a dependency among the previous stat, and previous stat is an input function of the model parameter theta. So you need to make the derivative multiple times path. But this is the detail. And another work in this year ICML is called input convex neural nets, which is very similar to the previous structure prediction energy network, except one thing: the design architecture of energy network. In this work, they designed the energy network to be convex with respect to the y. So the benefit of that is when you do the test time optimization, solving the inference problem, this will have a global optimal solution. Of course, to design the network to be convex, you have some assumption or say constraint need to make on the weight parameter w. So let me go to the experiment parts. In their for simplicity, we rerun the experiments in those ICML paper where they consider only these 3 relatively small scale multi-label data sets. The main reason why we want to rerun their experiments is that actually in their paper, they did not compare with the most strongest state-of-the-art multi-label text classification baseline. So we find interesting to compare with this. The setting is like this. The input feature representation is just 0 and 1 binary back and forth feature. And they pre-train the feature network based on the binary logistic loss. And the evaluation metric is precision at 135, which is commonly used in literature. So the results like here. Before jumping to the number, I would like to emphasize that the hybrid parameter for each method it's just follow the default setting, so I didn't heavily tune. And not so surprising, if you see the facts XML in the sleek, it's either facts XML or sleek that reach the best performance. However, if you look at the ICNM, this column here, you can see in the delicious dataset has the largest number of labels among these 3. It actually is the second best, outperformed the sleek and the PD sparse here. So the first column is just a multi-layer perceptron, and the second column and third column is using energy network. So they outperform the MLP, saying that exploring the joint representation between data and label does help. And so if you compare the third column to the second column, the difference is the design of the energy network. So it seems like designing that the energy network to be convex with respect to y have some advantages when you are doing the test time optimization, so that you can solve that through more high precision with respect to the prediction y. So that's have more benefit in the delicious dataset and the bookmark datasets. I think that's all. Conclude my presentation today. So in short, the first part is I introduced some alternative way to extract the feature representation via another way of convolution neural nets. And the second part is I introduced some recent work in ICML that used in structure prediction, but we also can apply them in multi-label text classification. And they may provide some alternative insights of exploring the label dependencies. Thank you.
Thank you so much. Are there any questions? Oh, yeah. Mane?
It's really nice to see deep learning approaches starting to do so well for extreme classification. I have a couple of questions though. The first one is about scaling.
Right.
So actually I just wanted to clarify that the largest data set available on the repository has actually 3 million labels, not 670K. But of course, internally, as Ed was also mentioning, we've gone beyond 100 million labels, well beyond that. So how do you see these kinds of approaches scaling to those kinds of label settings? So that was the first question. And the second is, as regards the accuracy, I was wondering if you had compared against DISMEC or PPD sparse or faster XML as well.
Okay, so maybe I can first try to answer your first question. So I think you are asking whether this kind of model architecture can scale to further larger label space. So currently, we are only using dimension reduction through the hidden representation here. So if the final output space, say the dimension of y go through, say 5 millions, then we may have some trouble because in terms of the complexity, it's linear with respect to the output space. So if we are trying to apply this kind of framework on even larger data set, we need to make the hidden representation, hidden layer even smaller. So currently I don't have any other more advanced solution building upon this deep learning neural nets to address that issue. And I think your second question is, did we compare with PD sparse and sleek or fast XML? Oh, you mean the PPD? No, we haven't compared with the PPD sparse and the DISMEC. Right. But we. Right. So because currently I'm not working on this. So this is the earlier work in this year. So currently I'm working on other projects. So the first author may have conduct some experiment on that part, but he hasn't update with me yet. Right.
Okay. There's another question. Yep.
Yeah, I find the way you do convolution really curious. So I was wondering like whether it's specific to the setting of multi-label extreme classification or is it like general? So for example, if you replace the way you do convolution in the original KIM-CNN, would you actually improve the performance?
So we only investigate that ablation test under the data set we use in the multi-label. So I can't really say what that would be beyond the multi-label data sets. So if you can see here, the difference of V2 and V3 is really the direction you do convolution. So actually in the Eurolex data set and the Amazon 670K, that does improve, but not so much in the Wiki 30K. So I think that also depends on the data sets. Right.
Yeah, thanks.